Hello students, welcome back. Now let's complete this notebook. We have only one final topic left. We discussed standardization theorem. If you do this computation, z equals x minus mu over sigma, then you're going to get the standard normal. Expected value is 0 and standard deviation is 1, so that we can look up the table. Let's use this for a little bit more realistic problem. No, still not there. I guess all the realistic problems are shifted over to the next chapter, the next module. Hey, it's okay. Let's stick with stupid problems just a little bit more. So, mean is 16.75 and the standard deviation is 0.451. All right. Now, we're going to find out this using the normal table. How do we do that? Excuse me, a wrong key. We do it by the standardization theorem. If you do this x minus mu over sigma, then you're going to get the standard normal. And you can use the table. So let's go ahead and do that. Mu, sigma are given. This one, let's adjust it. So this is x value, x minus mu over sigma. And that's 16.01 minus 16.75 over 0.451. And all these are decimals, so they're all approximates. And then as for this computation, well, I have calculator with me, so let me just copy and paste and calculate it. I'm getting negative 1.6408. I'm looking up the normal table, so I'm going to need only first two decimal digits. Negative 1.64, and therefore this probability that p is less than or equal to 16.01 is equal to probability that z is less than negative 1.64. And this one is available in the normal table. You see, z is standard normal. Remember, look up negative 1.64. Where's the table? Negative 1.64. 0, 1, 2, 3, 4. 0.0505. 0.0505. And that completes the problem. Here, I'm using random variables, so I use capital Z and capital X. Here, I'm looking at the real number, 1601, for my X value. So this value associated with that, so I use small font there. We typically call it Z score. But if you misuse the cases, I'm not going to take off any points, so don't worry too much about it. If you're interested still, then I'm telling you there's a subtle difference between one and the other. we are doing this for real number arithmetic, and this one is for random variables. So there you go. X minus mu over sigma. And then look up the table. That's what it ended up with. Is a visualization? Yeah, there is. So x less than 1601 versus z less than 81.6408 are actually the same. X is spread around mean of 16.75 with a standard deviation of 0.451. Z is spread around 0 with a standard deviation of 1. But if you scale accordingly, these are the same. And how do you scale it? There you go. That's a scaling mechanism. X minus mu over sigma. Are there more? Okay, how about this problem? Greater than 1703. Well, greater than 1703, so it's gonna be 1 minus less than that, right? And it's gonna be 1 minus of appropriate z-score computation. Z is less than, well, okay. Do you remember the formula number 1? X minus mu over sigma? Remember? X minus mu over sigma? So x is 1703. Mu is 16.75. And sigma is 0.451. If you calculate that, you're going to get z value that you should look up. Oh yeah, okay. Let me just take one more step. So let's calculate that. 0.62 something. Okay, all right. I'm going to use z tables, so I don't need any more than just 2 decimal digits, and everything is approximate anyway, so that's okay. And then let me calculate this. 1 minus you have to calculate this. Z is less than 0.62. Less than 0.62, where is it? Go there. 0.62. It should be in the second page. 0.62. 0.62. 0.7324. 0.7324. And that's got to be your computation. Let's see, what did I do here? So we are looking for this portion. So we have to get this and subtract from 1. And this, we got 0.7324. So 1 minus 0.7324. Do I end up with 0.2676? It looks like it. Yeah. Yes, 0.2676 is correct. Now, what if I want the probability in the middle? Well, it's going to be subtraction. This is what we want. And in terms of standard normal, it's going to be this one. If you apply that z-score computation, x minus mu over sigma, to this x1 and that x2, this and that, and those two numbers we did in part A and part B respectively. I hope you remember. So let's just use those. And that's nothing more than subtraction. This green minus blue. And oh boy, that's a computation we did before in the previous exercise. So what if you have a general normal random variable with mean and standard deviation? You can scale it and make it into standard normal by formula number 1, z equals x minus mu over sigma. Where is that formula? Right here, x minus mu over sigma. Formula number 1 in terms of the level of importance for this course. And then you can rewrite all these in terms of z, and then you can look up the table. Now, before looking up the table, make sure you draw the pictures, and the pictures will be considered as part of the justifications. Do you have enough time? I guess we have enough time for some inverse problems. How about these? Okay. Mu is 6.75 and sigma is 0.451. Again, the same problem, I guess. And then probability that x is less than something is 0.25. Well, look up the z table and get it. So from the z table, we can backtrace and find out your z-score accordingly. Let's see. Let's go back to your z-table, normal table. Where's 0.25? 0.25 right here. So we have 0.2514 versus 0.2483, somewhere in the middle. So that's negative 0.67 versus 8 is 7, 8, 9. So negative 0.75. Makes sense? 0.2514, 0.2483. So 25% must be somewhere in the middle. So 0.675, somewhere in the middle. That's my estimation. Negative 0.675. So negative 0.675. But then again, this is z, not x. So what is x? This z-score is actually x minus mu over sigma. Formula number 1, z is x minus mu over sigma, and mu value here is 16.75, and sigma value here is 0.451, and from here finding out x, it's just a linear equation. At 3000 level, this should not cause any kind of trouble whatsoever. So 0.675 Yeah, 449. I use a little bit more accurate number here in this mathematical computation. But when I looked up the table, I just estimated 60.75. That's okay. And then calculating x out from that equation, it's going to be this computation there. A little bit less accurate, but that's okay. And that's the x value you're looking for. There are more problems, but they are kind of like these, and I'm going to leave the details to the students. After all, the key part is x to z conversion or vice versa. For z, we have normal table, and x for z computation is just scaling. Z equals to x minus mu over sigma, that computation. So you can either set up and do direct computation, or set up and solve an equation. Hey, this is 3000 level, so that should not cause any kind of trouble. The key thing that I want to emphasize that everybody must remember is z table associated to the standard normal and is coming from the standardization theorem, x minus mu over sigma. Now, using the standardization theorem a little bit more to get more empirical problems, well, that's something we're going to discuss in the next lesson, in lesson 7. For now, we'll say lesson 6 is complete. And we'll meet again with a little bit more empirical and realistic problems in a separate section, separate lesson.